So let's get into today, which is all about Bernoulli and Leonard Euler as well, actually, and their equations that describe flow dynamics or properties or conditions of flow along a streamline. So Bernoulli was the first to verbalize, I guess, or say out loud, as it says here, the relationship between the pressure, velocity, and the elevation of a flowing fluid. And this is in his textbook back in 1738. So it's been around for a while. And then Leonard Euler, famous mathematician, came some little bit later, and he provided the complete derivation of the equation 20 years later. So what is this Bernoulli's equation? So first, let's just imagine a steady flow along a streamline. We discussed what a streamline was. So everywhere along the streamline, our flow is tangent to that streamline path. And imagine we're just on this little fluid element, and we can derive Bernoulli's equation from the force analysis of a particle of fluid moving along a streamline. So Bernoulli's equation can be derived from the force analysis of a fluid particle along a streamline. So here's our streamline. On the right, we have our red fluid particle. It has some length ds. It's one-dimensional. It's inclined at an angle theta with respect to the vertical direction. The pressure on the lower left-hand side would be P, and the pressure on the upper right-hand side would be P plus some change in pressure dP. And each of those ends has the area dA, and the total weight due to gravity of that fluid element is W. So let's apply Newton's second law. Newton's second law says that sum of the forces, and let's do the forces along the streamline, must be equal to the mass of the fluid times the acceleration of that fluid along that streamline. So let's solve for mass and acceleration first. So the mass is just equal to our density times the volume, and the volume would just be ds times dA. And our acceleration along that streamline is just our first time derivative of our velocity along that streamline. And we don't really know the direct derivative of our velocity with respect to time, so we can use the chain rule, and we can get the derivative of our velocity with respect to our position s times the derivative of s with respect to t. And we know that ds dt is just actually equal to our velocity. So we can write our acceleration is equal to dv ds times v. So finally, we can write our mass times acceleration term would be equal to our mass, rho, let's write it dA ds times v dv ds. So this we'll write as equation 1. So now let's look at the left-hand side of the equation, some of the forces along the streamline. So let's sum up the forces. So if we're looking at our coordinate, our S coordinate down here, that's along the streamline, we only care about the component of the forces acting along the streamline. So the force at either end, the left-hand side here, is in the positive S direction. So that would be P times dA. And the force on the right-hand side is minus P plus dP times the area. And then lastly, we have the component of gravity, which is the weight right here. And that weight would be mass times acceleration due to gravity. And we want the component that is acting in the S direction. So it's going to be acting in the negative S direction. And that would be the mass, just like before, rho g dA ds is our weight. And we want the component sine theta. So if we simplify this, we can get some of our forces. Let's write this down here a little bit bigger. Are equal to negative dP times dA, because our capital P times dA and capital P times dA here, you add 1, subtract 1, so we're left with 0. So all we're left with is the dP dA term minus the component of the weight in the S direction. So rho times G dA ds sine theta. And this is equation 2. This is the left side of the equation. So let's put these two equations together. I'll write them out here again. We have some of the forces in the S direction is equal to mass times acceleration in the S direction. Some of our forces was negative dP dA minus rho g dA ds sine theta. And this is equal to our mass times acceleration, which was rho dA ds times v dv ds. So that's equation 1 and 2. If we simplify this, we can get rid of a few terms. Let me try something. This keeps freezing on me, so. So if we simplify, we should end up with negative dp minus rho times g times dz is equal to rho times v times dv. So we get dz because our term ds times sine theta is equal to dz. So we look back at our equation here. ds is the length that's going along the streamline. The sine of theta times ds would just be the z component. So this is our basically differential form of our Bernoulli equation. And technically, it's actually right now in our Euler equation form. So let me show, just leave that a bit so we can see it a bit. If we rearrange this, we can get it into the steady flow Euler's equation. So we just put all of the terms on the same side and make them all positive, and we end up with dp plus rho v dv plus rho g dz is equal to 0. So this is our steady flow Euler equation. And then if our flow is incompressible, we can integrate Euler's equation along the streamline and we get Bernoulli's equation. So for incompressible flow, we can integrate along the streamline. So if we write out that integral, we have the integral of between 2 points, 0.1 and 0.2, so pressure 1, pressure 2 of dp, plus the integrand here, the next one is dv. So we have the integral from velocity 1 to velocity 2 along the streamline of rho times v times dv. And the third term is the integrand is dz, so we're integrating from elevation z1 to z2. Of rho times g times dz. And since these are definite integrals, there's no integration constant, so then this is still just equal to 0. So finally, if we evaluate this integral, we get Bernoulli's equation. So Bernoulli's equation is written in the form P divided by rho. Let's write this in black. P divided by rho, our pressure divided by our density, plus the velocity along the streamline, the fluid squared divided by 2, plus acceleration due to gravity times the elevation z is equal to a constant. And this finally is Bernoulli's equation. So we have two equations that are both valid, Bernoulli and Euler. The only difference between the two is if we have an incompressible flow, then we can integrate Euler's equation, assuming that our density rho is constant. If we have a flow that is compressible, then we have to assume that rho is changing with our pressure, with our velocity, with our elevation. So we would not get the same equation as Bernoulli equation. So Bernoulli is only valid when we have incompressible, and we should also say steady flow along a streamline. So we can write Bernoulli's equation between any 2 points, just like that integral suggests. So if we do that, we end up with a form of Bernoulli's equation, two different forms. So Bernoulli can be evaluated between any 2 points. On a streamline. So if we did that, one equation we could get, if we integrated that directly, the equation above, we get P2 minus P1 divided by rho plus 1/2 V2 squared minus V1 squared plus acceleration due to gravity times Z2 minus Z1. And this is equal to 0. Or if we wanted to rearrange this to a more common form, it's more common to see Bernoulli's equation written as P1 over rho plus 1/2 V1 squared plus G times Z1 is equal to the same equation at point 2. So P2 over rho plus 1/2 V2 squared plus G times Z2, which is equal to some constant. Just is constant. So it's not changing. So at any point along the streamline, this relationship will hold. That's what this equation up here is saying. So if we evaluate Bernoulli's equation at any point along a streamline and consider those 3 terms, the sum of those 3 terms will always be constant along that streamline. So let's break down these terms. These terms have a few components, and we can sort of describe what each of them means. So the first term, the pressure density, we call the flow energy. These are all energetic terms. They have the same units as energy. V squared over 2 is our kinetic energy of our flow. And then the gravity times our elevation is our potential energy. So potential energy stored in gravitational potential energy. So the Bernoulli equation verbally states that, if we think about what this means, the sum of the kinetic, the potential, and the flow energies of a fluid particle is constant along a streamline during steady flow. And I should also add incompressible. All right, can we go back? Where do we want to go back? Just here? Or one more slide up here? So yeah, to answer the question in the chat, can we apply this equation to more than 2 points at the same time? Yeah, so if this is steady flow, that means the flow characteristics is not changing with respect to time. So at any point in time, we can measure this flow as long as the flow is steady, and you can evaluate this at any point along a streamline. So every point along that streamline continuously should follow this relationship. And this is actually what you'll be using in your first lab, your Venturi lab. You'll need to use Bernoulli's equations and continuity equations and flow in a Venturi meter, which is all derived from Bernoulli's equations. So let's look at these terms. If we take, let's go back up a little bit. If we take these terms and we multiply, divide each term by the acceleration due to gravity, g, then we can get the terms in terms of pressure heads. And we can find another interpretation of Bernoulli's equation. So if each term refers to a form of energy in the fluid, each term refers to a form of energy in the fluid per unit weight. So in SI units, energy per unit weight in our units for SI, that would be energy would be newtons times meters divided by newtons for our weight. Divided by newtons, which would just leave us with meters. So if we rewrite this, we can express the terms in terms of height, or in fluid terms, height would be called head. So we can express in terms of pressure head. So we can get P1, if we divide this by G, we have rho down there, rho times G is equal to our specific weight, gamma, plus V1 squared over 2G now, plus just our elevation Z. And then the same thing for point 2, P2 over gamma plus V2 squared over 2G plus Z2 is equal to some constant. So this term here is our pressure head. Same as we had before when we were looking at manometer fluid heights. We also have a velocity head. So that's the head pressure just due to the velocity of the fluid. And then our third term is our elevation head. So in the chat, for the equation, are there meant to be two equal signs? Are you referring to this equation right here? Or this equation here? I guess they're the same equation. So all we've done in the other one is we've divided this equation here by g. So each of these terms is for point 1, and then over here could be some other point along the streamline, point 2. So all the constant is saying, I don't mean that it's some constant, it's always the same number. I'm just saying for any point along a streamline, this quantity won't change. The quantity is constant. So if we know the pressure, P1 divided by rho, and we take 1/2 of the velocity squared at that point in the streamline, and then we take the elevation and multiply it by g, the value that we get will be the same value that we get if we did that for any other point along the streamline. So the constant here is not a specific constant. It's just saying that this expression is constant. It will not change anywhere along the streamline. So here it is again, where we have the term P divided by rho g, where rho g is just equal to gamma. That is called the pressure head, and it represents the height of a fluid column that produces the static pressure P. V squared over 2g is the velocity head, and it represents the elevation needed for a fluid to reach the velocity v during frictionless freefall. So if we had a fluid and it is falling some distance, how far does that fluid have to fall, ignoring any effects of friction, before it reaches that velocity? That's what that head represents. And then z, the elevation head, represents the potential energy of the fluid. So we can relate these, and this is used a lot in the fluid terms, to something called an energy grade line and a hydraulic grade line. So let's first describe what the energy grade line and hydraulic grade lines are. So the energy grade line, the energy grade line shows the height corresponding to all heads. And the hydraulic grade line shows the height corresponding to elevation and pressure heads. Shows the height corresponding to elevation and pressure heads. So if we look at our equation and we look at the terms, the hydraulic grade line over here, let's look at point 2, only considers our pressure divided by rho g plus our z elevation. And if we add on the last term, which is our velocity, we get our velocity head as well, which is part of our energy grade lines. Energy grade line, I think, is the total energy, and the hydraulic grade line think of as the static part. So if we write out Bernoulli's equation again, we would see P over gamma plus V squared over 2G plus Z is equal to a constant. So what is constant? So our energy grade line is the whole term, the whole expression, and the hydraulic grade line is just the first and last terms. So if we had a pipe, maybe we had a gas line or a water main or something like that, and we were to put in these taps that we show in this picture. So let's show here, we have some taps that open up in the middle of the flow, and we have some taps that are at the right at the edge of that pipe. Taps that are at the edge of the pipe would be showing our static pressures and our elevation pressures, so that would give us our hydraulic grade line. And if we had our tap going to the middle of the flow, we would have our energy grade line. So can anyone think of why a tap at the sidewall versus a tap in the middle of our flow would show a difference? Why is the middle of the flow show that velocity component, and why does the edge of our flow along that the wall not show the velocity? Right, because of that no-slip condition. So right along the wall of our pipe, because of the no-slip condition, the velocity along the walls of the pipe must be 0. So if the velocity is 0 at the edge of the pipe, the only pressures that we're measuring, the only heads that we would see at the edge of that flow would be our elevation head and our pressure head. Our velocity head, we would have to look at the pressure in the middle of our flow, which would include the velocity of our flow. Good. So let's look at an example now. So this example, we just have water at 20 degrees C flows along the streamlines shown below. So I haven't shown them below, but let's just say these are streamlines. And we have 0.1 and 0.2. So the gauge pressure, velocity, and elevation at 0.1 are 15 kPa, 1 meters per second, and 5.02 meters, respectively, and the velocity and elevation at 0.2 are 0.5 meters per second and 5.21 meters, respectively. So it's asking estimate the pressure at 0.2. So if we apply Bernoulli's equation, let's write down what we know for 0.1. At 0.1, we have (15 kPa). Our velocity at 1 is 1.0 meters per second. And our elevation Z is 5.02 meters. At 0.2, we don't know pressure. We're asked to find that. We know V2 is half, so it's 0.5 meters per second. And our elevation is 5.21 meters. So if we write out Bernoulli's equation, P1 over gamma plus V1 squared over 2 times G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. So if we write down all the values that we know, 15.0 divided by gamma for water at 20 degrees C is 9.789 kilonewtons per meter cubed. I'll write that over here. Plus our velocity, so 1.0 squared divided by 2 times 9.81 plus 5.02 is equal to our unknown pressure 2 divided by 9.789 plus 0.5 squared over 2 times 9.81 plus 5.21. So if we solve this, we get P2 is equal to 13.5 kPa. So according to Bernoulli's equation, if we have an incompressible fluid, we have liquid with water, so it's probably incompressible. That's a good assumption. And if it's steady along a streamline, so we have to assume that it's a steady flow, then our pressure at point 2, if it decreases its velocity and increases its elevation a little bit, would be 13.5 kPa. So let's consider some limitations of Bernoulli's equation. We talked quickly just about some of the assumptions that we made when we integrated Euler's equation to get Bernoulli's equation. So one of the assumptions was that we had steady flow, which means that the flow conditions are not changing with respect to time. So Bernoulli's equation is only applicable if we have steady flow. That means our properties and the conditions can't change with respect to time. The flow must also be along a streamline. So because we derived those equations for flow along a streamline, the Bernoulli's equation is only applicable for flow along a streamline. So you can't take one point on a different streamline and compare it to a point somewhere else in the flow that isn't the same streamline. And Bernoulli's equation will not give you accurate results. We also have to assume that the flow is frictionless or inviscid. So it's only applicable if we have frictionless flow. Because we wrote it in that energy term, we don't have any energy terms to account for losses due to friction. So as Bernoulli's equation is written so far, it only is valid for frictionless or inviscid flow. Likewise, we can't account for losses. We also can't account for external work being done to the flow. So it's not applicable for any flow sections that involve a pump, a turbine, fan, heat exchanger, something that is putting energy into or taking energy out of the flow. It cannot work for compressible flow, so it is only valid for incompressible flow. When we integrated Euler's equation, we assumed that the density was constant, so it's only valid for liquids and gases that are at low velocities where we can assume incompressibility. And then again, similar to no external work, there can't be any heat transfer because the properties of the fluid would change with temperature. We should not be using Bernoulli's equation for any flow sections that involve a significant temperature change. So why can't we consider frictionless effects? So frictionless effects, heat transfer, and components that disturb the streamline structure of flow make the Bernoulli equation invalid. So examples of this would be the top left here, a sudden expansion. So we no longer have steady flow in that region, and so it breaks down, we can't use it. There's too many losses, energy loss in a system like this. If we have a long, narrow tube, over that distance, the frictional forces, the viscous forces along that wall would be significant enough that we would have to consider those losses, and Bernoulli's equation wouldn't be accurate. The values at point 1 would no longer equal the values at point 2 because there would be some loss. And then if we think of the opposite way, when we look at the fan at the bottom, we are inputting energy into our system between point 1 and point 2. And Bernoulli's equation, as written, doesn't have any way to account for that input energy. So we can't use it for flow across some sort of power input device. And same thing with the heat section. We cannot use Bernoulli because the properties of our fluid are changing as we increase or decrease the temperature. So our temperature must remain more or less constant throughout that flow. And then lastly, this one may be a little bit less obvious. If we have a flow through a valve or some device with sharp geometry, they have losses, and because there's a large amount of friction in the flow, and that frictional loss, we can't account for it, so we can't use Bernoulli's equation for sections of flow that cross a valve, for example. So if Bernoulli's equation is approximate and valid only in inviscid regions of flow, then in general, frictionless effects are always important very close to solid walls. So we call that inside the boundary layer, like we talked about last lecture. Inside the boundary layer is where frictional effects are the highest. And as we get further away and we leave the boundary layer, we more or less have a steady and uniform flow. So our viscous forces are very small. So Bernoulli's approximation is typically useful in the flow regions outside of the boundary layers and wakes only. So if this is our flow right here, at the very beginning, we would have our boundary layer forming, and that boundary layer might increase as we go further down our airfoil, for example, and then there might be a trail leading behind. So this we would call a wake. And the wake would essentially be our boundary layer region after it has left our body. And if it's still along the surface, this is our boundary layer. And so outside of our boundary layer, we would have our streamlines. Might look something like this. So Bernoulli is valid here. And it is not valid here. So if we have a flow device or some object that is moving through a fluid or flow moving around an object, our Bernoulli equation is not valid within that boundary layer. So let's look a little bit closer at the pressures in Bernoulli's equation. So let's write it back in our pressure form that we had originally. So we had P plus 1/2 rho V squared plus rho G times Z. So this is another rearrangement of the equation, and we can think of Bernoulli's equation in terms of pressures. So we could look at it in terms of energies, we can look at it in terms of pressure heads, and we can look at it in terms of pressures. So the first term, P, is static pressure. And this is the actual pressure or normal stress in the fluid. The next term, which is 1/2 rho v squared, this is called our dynamic pressure, which is the pressure associated with the velocity of the fluid. And then lastly, P0 which we'll define in a second, is something called our stagnation pressure. And the stagnation pressure is the static pressure at the point where the fluid is brought to rest. So if we were to take a flowing fluid and we were to keep all conditions the same except for we were to bring the velocity to 0, then that would be our stagnation pressure. And we'll show in a second what that equals to in terms of Bernoulli's equation. So is the pressure at the point where the fluid is brought to rest, which makes sense. We set our stagnation point in the flow as the point in our flow where we have 0 velocity. So at our stagnation point, we have our stagnation pressure. Pressure at the point where the fluid velocity is 0. So what is P0? Well, if we use Bernoulli's equation at the top, and we say this is equal to a point in the flow down the streamline after the velocity has been brought to 0, all we're left with is two terms, sorry, P0, pressure at the stagnation point. Our velocity is 0, and we only have rho gz remaining. And if we have no change in elevation, then our rho gz on both sides will be equal. So our P0 is left over equal to pressure times 1/2 rho v squared. So the pressure of the fluid at some point plus 1/2 rho v squared at that same point. So at any point in the flow, if we know the pressure and the velocity, the stagnation pressure is the sum of those first two terms. So let's show a bit more about this. So where is stagnation pressure in a flow? Well, if we look at an airfoil, the leading edge, the point, the streamline that would go directly into the leading edge of that airfoil would be our stagnation point, because the flow would come to a stop right at that point, and then any streamline slightly above or below it would be diverging around that airfoil. So there is some point at that leading edge. That is our stagnation point. So from the chat, is V different than the fluid velocity? Because wouldn't the second term be 0 otherwise if V was equal to 0? So let's go back. Actually, let's just write it again down here. So let's go into this. If we want to take 2 points, let's take point 1. And let's say our stagnation point over here is point 2. Or to make it simpler, let's just call it point 0. So let's write Bernoulli's equation for this stagnation point. So we have P1 plus 1/2 rho V1 squared. And if we assume the change in elevation here is negligible, let's just ignore that Z term for now. Or we could just include it just to be complete. Rho times G times Z1. And this would be equal to P0 plus 1/2 rho V0 squared plus rho GZ0. So if Z1 is equal to Z0, so you have no change in elevation, and V0 is equal to 0 because it's our stagnation point, then we can rearrange this equation and we get some terms go away. So this term will go to 0. These two terms cancel out. And all we're left with is P0 is equal to P1 plus 1/2 rho V1 squared. Try to write that a little neater. So this is a combination of our static pressure and our dynamic pressure. Let's show it in blue. And our dynamic pressure. So all that's happened is a fluid element along that streamline. At some point 1, it had a pressure, a velocity, and at some point 0, the velocity slowed down to 0. So it wasn't moving anywhere. We're at a stagnation point along the same streamline. And at that point, the only term we had left is our P0, and that is our stagnation pressure. It's not true that the heights will always be the same. So if we were measuring pressure along a streamline and that streamline, say, was increasing in elevation, then we would have to consider that Z term. But for this example here, if we're assuming our coordinates maybe look like this, maybe this is X, and this is Z, then the Z elevation between those 2 points might be the same. So we would have to consider that, but generally speaking, if we're measuring these 2 points in a certain kind of device called a pedostatic tube, which we'll get to later, the Z component goes away because they're always held horizontally when they're measuring flow. So let's look at some simplifying assumptions for solving different kinds of problems where we might have flow in tanks, reservoirs, or nozzles. We're assuming for these that they're exposed to the atmosphere. So if this is the case, we have two simplifying assumptions that can help make our problem solving a bit easier. So when the fluid at a point is exposed to the atmosphere, pressure is 0, and the corresponding term is canceled from Bernoulli's equation. So when the fluid at a point is exposed to the atmosphere, the pressure is 0 and the corresponding term is canceled from Bernoulli's equation. So that's our first assumption. So essentially, we have our flow exposed to the atmosphere. We really only care about the gauge pressure. So any point in the flow that is at the atmospheric pressure would just have a pressure of 0. The next assumption is that the velocity head at the surface of a tank or reservoir is considered to be 0, and it's also canceled from Bernoulli's equation. It's called BE Bernoulli's equation. Okay, so let's do an example. So this question, it asks, a large tank open to the atmosphere is filled with water to a height of 5 meters from the outlet tap. So the distance from the outlet tap at point 2 to the surface is 5 meters. The tap at the bottom of the tank is now opened and water flows out from the smooth rounded outlet. So smooth here just means that we don't have to worry about any friction. Determine the maximum water velocity at that outlet. So where do we start with this question? Just to go back to the chat, just has to go up a bit. So where can we start with that question? We have a tank, a reservoir with water, and there's a tap at the bottom. It's opened up, and it's asked, what is the maximum velocity at the outlet? So we should first start off by writing some assumptions. If we're going to use Bernoulli's equation, we need to assume that we have incompressible flow. And it is steady. And we have to assume that we can neglect any losses at the tap. Since that tap has a valve, there's a flow device, Bernoulli's equation might not be valid, but if we assume, like it says in the question, that it's smooth, then we can say maybe those losses are so small that they're insignificant, so we can just ignore them. So let's write what we know. If point 1 is at the surface of our fluid, right here, and point 2 is at our tap, down here, what is the pressure at point 1? Anybody? Yeah, it's atmospheric pressure. So we can just say it's equal to P atmosphere. And our velocity at point 1? Yeah, our velocity at the surface, it's not really flowing. We're assuming it's static. We're assuming the reservoir is so large that the velocity anywhere from that reservoir emptying will be negligible. So the velocity at the top, 0 meters per second. And our Z1 is at the top. So that's, if we measure with respect to point 2 or the bottom of the tank, then our Z elevation is 5 meters. So at point 2, our pressure is, what's our pressure at P2? Our static pressure. Yeah, we'll answer your question, Callie, in the chat once we write out Bernoulli's equation, and we'll see which terms just go to 0. So our static pressure at point 2 is just our atmospheric pressure. Because it's exposed to the atmosphere of the fluid at point 2, as soon as it leaves that tap, is exposed to the atmosphere, the pressure is going to be the atmospheric pressure. And our velocity at point 2, we don't know this. This is what we're asked to find. And our Z value, our elevation at point 2 is equal to 0. Because we're saying that this is our reference level. So if we write Bernoulli's equation, we would get P1 plus 1/2 rho V1 squared plus Z1 is equal to P2, or sorry, not just Z1, rho G Z1. which is equal to P2 plus 1/2 rho V2 squared plus rho G Z2. So in this equation, our pressures, P1 and P2 are both atmospheric pressures. So they're the same, and they were just equal to 0. So these can go away. Our velocity at point 1 is 0, so that term goes away. And our elevation at point 2 is 0, so that term goes away. So all we're left with is these two terms here. So we get V2 squared is equal to our rho's density cancels out, and all we have left is 2 times G times Z1. So V2 is equal to the square root 2G Z1. Which is the square root of 2 times 9.81. And Z1 is 5. So our velocity, 9.9 meters per second. So that would be the velocity of the fluid leaving that tap. Good. So that's the first half. That was basically developing Bernoulli's equation, applying it to a simple problem. Next half of today's lecture, we'll be looking at some applications of Bernoulli's equation and some flow devices that make use of Bernoulli's equation to actually measure flow. So our quote for the first half today is from Qui-Gon Jinn, and there's always a bigger fish.